Open and closed sets. A subset X of the set of real numbers is said to be open if for every real number, little x in big X, there's an open interval AB with little x in AB and AB a subset of big X. In words, a set is open in the set of real numbers if every number in the set has some space on both sides of that number inside the set. If you think of each point in the set as an animal, then each animal in the set should be able to move a little to the left and a little to the right without ever leaving the set. Another way to think of this is that no number is on the edge or the boundary of the set about to fall out of it. Let's look at some examples. Every bounded open interval, AB, is open. For example, the open interval from 0 to 1 and the open interval from -√2 to 3/5 are both examples of open sets. To see this, let X equal the open interval from A to B, and let little x be in big X. Then big X, in other words, the open interval from A to B itself, is an open interval with little x in AB, and AB a subset of X, because every set is a subset of itself. In fact, all open intervals are open sets. For example, the infinite open interval (-2 to infinity), the infinite open interval (-∞, 5), and the real line (-∞, infinity) are all open sets. Let's show that the infinite interval A infinity is an open set. The idea is simple. If X is in A infinity, then AX plus 1 is an open interval with X inside of it, and with AX plus 1 a subset of A infinity. Showing that the infinite open interval (-∞) B is an open set is similar. As a non-example, the half open interval 0 to 1, including 1 and excluding 0, is not an open set because the boundary point 1 is included in the set. If AB is any open interval containing 1, then that open interval AB is not a subset of the half open interval 0, 1, because there are numbers greater than 1 inside the open interval AB. For example, if we let X equal 1/2 of 1 plus B, in other words, we're just taking the average of 1 and B. Since B is greater than 1, we have that X is greater than 1/2 times 1 plus 1. Notice how I'm using the first property of an ordered field here to do this. That's equal to 1/2 times 2, which is 1. So X is greater than 1. Also, since 1 is greater than A, right, because 1 is inside the open interval from A to B, in particular 1 is greater than A, we have that X is greater than A, right, because X is greater than 1 and 1 is greater than A, so X has to be greater than A. Now, since 1 is less than B, we have that X is less than 1/2 B plus B, again using the first order property for an ordered field. That's equal to 1/2 times 2B. By associativity in the field of real numbers, that's 1/2 times 2 times B. 1/2 times 2 is 1, so we get 1B. And since 1 is the multiplicative identity, that's equal to B. So X is in the open interval from A to B. In fact, all half-open as well as closed intervals, are not open sets. Theorem 6.3. The empty set is an open set. The proof of this is pretty straightforward because the statement that the empty set is open is vacuously true. Since the empty set has no elements, there's nothing to check. Again, when there's nothing to check, we call that being vacuously true. Theorem 6.4, the set of real numbers is an open set. Let's prove this. If x is a real number, then x is in the open interval from x minus 1 to x plus 1, and that open interval is a subset of the set of real numbers. Since x was an arbitrary element of R, we have shown that for every x in R, there's an open interval AB with x in AB, and AB a subset of R. So R is open. Theorem 6.5. A subset X of R is open if and only if for every real number, little x and big X, there's a positive real number C such that the open interval x minus c to x plus c is a subset of big X. Now, I just want to mention that the second half of this theorem is what many authors use as the definition of what it means to be open. I prefer to use the definition that I introduced earlier because it's a little bit simpler and doesn't have the added complexity that the open interval that you're choosing that contains X has to be centered at X. But it's nice to know that the definition we've been using is equivalent to the definition that is introduced in most analysis and topology textbooks. Let's give an analysis of the harder part of this theorem. The harder direction of the proof is showing that if X is open, then for every real number, little x and big X, there's a positive real number C such that the open interval x minus c to x plus c is a subset of big X. To see this, suppose that big X is open and let little x be in big X. Then, by the definition of open, there's an open interval AB with little x in AB, and AB is a subset of big X. We want to replace the interval AB by a different interval, potentially, that has little x right in the center. Here's a general picture of what might have happened when we chose our interval AB. There are really three cases. X could have wound up at the center, in which case there's nothing to prove, but also X could have wound up to the left of the center or to the right of the center. In this particular picture that I drew, X wound up to the left of the center. Okay. In the picture, we have an open interval AB containing little x. In this particular picture, little x is a bit closer to A than it is to B. However, we should remember to be careful that our argument doesn't assume this, because we have no control over where x sits inside of the interval AB. We just know that there's some interval AB containing x. Like I said, x could wind up at the center if we're lucky, but more likely it's going to wind up either to the left of the center or to the right of the center. In this particular picture, it wound up to the left of the center. X minus A is the distance from A to X. And B minus X is the distance from X to B. Since the distance from A to X is smaller, let's just let C be that smaller distance. So C is X minus A. From the picture, it looks like the interval X minus C, X plus C will be inside the interval AB. In general, if x is closer to a, we would let c equal x minus a. And if x is closer to b, we would let c equal b minus x. We can simply define c to be the smaller of x minus a and b minus x. We write that as c equals min, for minimum, of x minus a, b minus x, in brackets. From the picture, it seems like with this choice of c, the interval x minus c, x plus c, should give us what we want. Okay, I think we're ready to write out the proof now. Let capital X be an open subset of R, and let little x be in capital X. Then there's an open interval AB with x in AB, and AB a subset of big X. Once again, here's the same picture that I had before, just to guide us through the rest of the argument. We're going to let C be the minimum of little x minus a and b minus little x. We claim that x minus c, x plus c is an open interval containing little x and contained in the interval AB. So to prove this claim, we need to show this sequence of inequalities, that a is less than or equal to x minus c, which is less than x, which is less than x plus c, which is less than or equal to b. Okay, so we're going to go through each of these inequalities one at a time, and that will show both that x is between x minus c and x plus c, which means that it's in the open interval, and also that a is less than or equal to x minus c, and x plus c is less than or equal to b, which gives us the other part, that x minus c, x plus c is a subset of AB. Okay, so first let's show that a is less than or equal to x minus c. Since c is the minimum of x minus a and b minus x, that means that c is less than or equal to both of those things. The one we need right now is that c is less than or equal to x minus a. As a consequence of the properties of the reals being an ordered field, we have that negative c is greater than or equal to the negative of x minus a. It follows that x minus c minus a is greater than or equal to x minus a minus a. Notice how I replaced the minus c by minus x minus a with a greater than or equal to symbol using the first order property of an ordered field. Okay, and this is equal to x minus x plus a, distributing that minus sign, which is a minus a, which is 0. So x minus c minus a greater than or equal to 0 is equivalent to x minus c greater than or equal to a, or equivalently a less than or equal to x minus c, which is what we just wanted to show. Great. Next, we'll show that x plus c is less than or equal to b. The argument is similar. Again, since c is the minimum of x minus a and b minus x, in particular, we have that c is less than or equal to b minus x this time. So again, we have negative c is greater than or equal to the negative of b minus x, and it follows that b minus x plus c distributing is equal to b minus x minus c, which is greater than or equal to b minus x minus b minus x, which is 0. So again, that's equivalent to b greater than or equal to x plus c, or equivalently x plus c less than or equal to b. So we've now shown that x plus c is less than or equal to b. Note that x is greater than a, so that x minus a is greater than 0. And x is less than b, so that b minus x is greater than 0. Since c is the minimum of two things which are both greater than 0, c is also greater than 0. Okay, now we're ready to show that x minus c is less than x. Well, simply have x minus c is equal to c, which is greater than 0. So x is greater than x minus c. And finally, we'll show that x is less than x plus c. we also have x plus c minus x is also equal to c, which again is greater than 0, so that x plus c is greater than x. There, we showed it. Okay, so we've shown what we wanted. We've shown that a is less than or equal to x minus c, is less than x plus c, is less than or equal to b as desired. Since x minus c, x plus c is a subset of the interval AB, and AB is a subset of big X, by the transitivity of the subset relation, we have that x minus c, x plus c is a subset of big X. The converse for this theorem is immediate, since for little x and big X, x minus c, x plus c is already an open interval containing little x. Theorem 6.6. The union of two open sets in R is an open set in R. Let's look at the proof. Let A and B be open sets in R, and let little x be in the union of A and B. By the definition of the union, x is in A or x is in B. Without loss of generality, we may assume that x is in A. What do I mean by this statement without loss of generality? This expression can be used when an argument can be split up into two or more cases, and the proof of each of the cases is nearly identical. For this proof, the two cases are x is in A and x is in B. Right? So technically speaking, we have to do each of those cases separately. But because the arguments are essentially the same, we could use this without loss of generality statement to cut our work in half. Okay, so the argument for case 2 is the same as the argument for case 1, essentially word for word, only the roles of A and B will be interchanged. Now, so we're assuming that x is in A. Since A is open in R, there's an interval AB with x in AB, and AB a subset of A. Recall that A is a subset of the union of A and B. So again, since the subset relation is transitive, and we have AB is subset of A and A is subset of A union B, follows that AB is a subset of A union B. Therefore, A union B is open. Let's look at an example. So we know that the open interval -5, 2 is open. And we know that the open interval 7 infinity is open. Therefore, by theorem 6.6, the union of these two open intervals is also open. Theorem 6.7. This theorem is going to generalize theorem 6.6. Let X be a set of open subsets of R. Then union X is open. So this theorem says that we could take the union of as many open sets as we want, and we still wind up with an open set. Let's write the proof. Let X be a set of open subsets of R, and let little x be in the union of big X. Then, by the definition of union, little x is in A for some A in big X. Since A is open in R, there's an interval AB with x in AB, and AB a subset of big A. Now, it's pretty easy to show that A is a subset of union X. You should definitely check this, though. This is a little set theory proof that is very short, and it will really test your understanding of these bigger unions as well. So it's definitely a good idea for you to go through that argument. Okay, since the subset relation is transitive, notice we have AB a subset of big A a subset of union X. It follows that AB is a subset of union X. Therefore, union X is open. Okay, I'm just going to push this theorem to the top so we have a little room for some examples. first example, if we just take the union of a bunch of open intervals, that's going to be open. For example, 1, 2, union 2, 3, union 3, 4, union 4, infinity is an open set because it's a union of open intervals, which are each open. As a sort of bigger example, R minus Z is open because it's a union of open intervals, this time infinitely many open intervals. It looks like this, right? So we have all these open intervals leading up to -2, -1, union -1, 0, union 0, 1, union 1, 2, and so on. Another way we could write it as the union of the set of intervals n, n plus 1, such that n is an integer. And one other notation we could use is the union of n and z of the interval n, n plus 1. One more example. If we look at the union of the intervals 1 over n plus 1, 1 over n, where n is a positive integer, that's going to look something like this. We have ... union 1/5, 1/4, union 1/4, 1/3, union 1/3, 1/2, union 1/2, 1. Notice how the infinite part goes infinitely sort of inward towards 0. Well, this is open because it's an infinite union of open intervals. Theorem 6.8. Every open set in R can be expressed as a union of bounded open intervals. Let's prove this. Let big X be an open set in R. Since big X is open, for each little x in big X, there's an interval a sub little x, b sub little x, with little x in that interval a sub x, b sub x, and a sub x, b sub x, a subset of big X. Okay, notice I just indexed these intervals by little x because there's one of these intervals for every single little x in this set big X. We're going to let y be the set of all these intervals a sub x, b sub x, where little x is in big X. And we'll show that x is equal to union y, which will complete the proof. To show this, we're going to use the axiom of extensionality and show that each of these sets is a subset of the other one. We'll start by showing that big X is a subset of union y. So we'll let little x be in big X. Then by the definition of these intervals, we have that little x is in the interval a sub x, b sub x. Since a sub x, b sub x is in y, again, by definition, little x is in union y. Since little x was arbitrary, we just showed that big X is a subset of union y. Now for the other direction, we'll take little x in union y. Then there is some z in x, big X, with little x in a sub z, b sub z. Since a sub z, b sub z is a subset of big X, little x is in big X. And since little x in big X was arbitrary, union y is a subset of x. So since x is a subset of union y and union y is a subset of x, by the axiom of extensionality, it follows that these two sets are equal. X is equal to union y, and that's what we wanted to show. Theorem 6.9. The intersection of two open sets in R is an open set in R. Let's write out the proof of this. Let A and B be open sets in R, and let little x be in the intersection of A and B. Then little x is in A, and little x is in B. Since A is open, there's an open interval AB with x in AB, and AB a subset of big A. And since B is open, there's an open interval CD with x in CD, and CD a subset of big B. Let C be the intersection of these two open intervals, AB and CD. Since X is in AB and X is in CD, X is in the intersection of them, or X is in C, big C. C turns out to be an open interval. This is something you should prove, that the intersection of two open intervals is either empty or another open interval. In this case, it's not empty because X is in the intersection because it's in both A, B, and C, D. Okay, so again, this is something you should definitely check on your own. Since C is a subset of A and C is a subset of B, again, this is another thing you should check, that both of these statements are true. It follows that C is a subset of the intersection of A and B. And again, one more thing you should prove. All these are very short set theoretical arguments that you should go through to make sure that you understand all of this. Okay, since little x in A intersect B was arbitrary, A intersect B is open. Here are a couple of exercises that will help you solidify the ideas from this section. One, the intersection of not only two open sets is open, but the intersection of finitely many open sets in R is an open set in R. And two, an arbitrary intersection of open sets in R does not need to be open in R. These are two things that you should try to show are true. We're going to finish up this lesson with a brief discussion of closed sets. A subset X of R is said to be closed if R minus X is open. R minus X is called the complement of X in R, or more simply, just the complement of X. It consists of all real numbers not in X. Let's look at some examples. Every closed interval is a closed set. For example, the closed interval from 0 to 1 is closed because its complement in R is the union of the two infinite open intervals, negative infinity 0, union 1 infinity. This is a union of open intervals, which is open. Similarly, the infinite closed interval 3 infinity is a closed set because the complement of it is the infinite open interval, negative infinity 3, which is open. As a non-example, half-open intervals are neither open nor closed. We have seen, for example, that the half-open interval 0, 1 is not an open set. We also see that it's not a closed set by observing that its complement is the union of the infinite closed interval, negative infinity 0, and the infinite open interval 1 infinity. And this is not open, right? It contains the boundary point 0. The empty set is closed because its complement, R minus empty, is R, which is open. Similarly, R is closed because its complement, R minus R, is empty, which is open. The empty set and the set of real numbers are the only two sets of real numbers that are both open and closed. Theorem 6.10. The intersection of two closed sets in R is a closed set in R. Let's prove this. Let A and B be closed sets in R. Then the complement of A and the complement of B are open sets in R. Since the union of open sets is open, the union of these two complements is open in R. So the complement of that union, R minus A union R minus B, is closed in R. Therefore, it suffices to show that the intersection of A and B is equal to R minus A union R minus B, because we already know that the one on the right is closed, and we want to show that the one on the left is closed. We're going to do this with a sequence of if and only ifs. X is in the set on the left, A intersect B, if and only if X is in A and X is in B. If and only if X is not in the complement of A and X is not in the complement of B. If and only if X is not in the union of these complements. If and only if X is in the complement of that whole set, R minus A union R minus B. Okay, so we just showed that A intersect B is equal to R minus A union R minus B, completing the proof. And I'm going to finish up by just mentioning a few exercises that you might want to do to solidify your understanding of closed sets. One, an arbitrary intersection of closed sets in R is closed set in R. Two, the union of finitely many closed sets in R is a closed set in R. And three, an arbitrary union of closed sets in R does not need to be closed in R.